Good day everyone, my name is Aparna Radhakrishnan. I'm from Princeton's Cooperative Institute for Modeling the Earth System and also stationed at NOAA's Geophysical Fluid Dynamics Laboratory. In this tutorial, we'll be talking about community-developed data exploration for Earth system model output and beyond. This is going to be at a very introductory level. The three main takeaways from today's tutorial is going to be understanding why we need data catalogs. Number two, what do we mean by data catalogs? What does the structure look like in context of a Python package called intake-esm? Third, we will also be looking at a Jupyter notebook that uses data catalogs to show its use in a simple analysis. In this slide, what you're seeing are the results from a survey that was conducted to see where or how the data scientists spend their time. And this study revealed that 80% of their time was spent on data preparation and data management aspects. In fact, 60% of the time was spent on data cleaning and data organization. 19% of the time was spent in the collection of the actual data sets. This really calls for improving the landscape that we have for exploring the data so that organization of the data and the data management side of things could be a little more enjoyable as a data scientist. Hope that gives you some context as to why we need data catalogs. We are dealing with big data archive and we want the data management, data search process to be much more efficient and enjoyable. Before I talk about intake-esm, let me acknowledge a few community collaborations here. First, Pangeo. Pangeo is a community platform for big data geoscience. Some of the Pangeo developers and other developers gathered for a CMIP 6 hackathon in 2019 where the users asked how they could search for data, how they could load the search results also in their multi-model analysis in an existing Jupyter notebook that perhaps uses Xarray and Dask to speed up the computations. How can the search be integrated with a framework that they're already familiar with and which is also powerful? This is when intake-esm was introduced. Lots of discussions that took place in the informal Pangeo and ESGF Cloud Data Working Group talking about how these catalogs can be structured so they are more standardized. And also other collaborators like NCAR, DKRZ and NOAA's Model Diagnostics Task Force who have also adopted the use of intake-esm in their workflows. So what is intake-esm? Intake-esm is a Python package which helps us query for information, search for information about data collections. Not only does it help in search, it also loads the search results in an Xarray dataset object. We won't be talking too much about Xarray today, but Xarray is a Python package that helps us work with labeled multi-dimensional arrays and absolutely suited for the NetCDF and ZAR datasets that we may be familiar with. It also is capable of understanding climate and forecast conventions, which is why it's helpful in writing standardized data analysis packages also. So when we talk about data catalogs in intake-esm, we are often talking about two different components. One is the catalog specification and the second is the catalog itself. The catalog specification is usually a JSON file. Here you find information about what do we expect to find in a data set. Is it going to be a NetCDF file? It's going to be a ZAR object. It also tells us what metadata can be expected to describe this data set, for which the details can be found in the catalog file, which is the CSV file. So back to the catalog specification, it also helps us understand how multiple files should be aggregated, should be concatenated, such that we can look at it as a single dataset when we're working with our analysis script. This is one of the key aspects of intake-esm, the ability to aggregate multiple files across a particular dimension, for example. Catalog specification can also provide information on additional metadata that one can expect in the catalog without actually opening the data sets themselves. The catalog, on the other hand, like I mentioned, it's a CSV file. It's a simple CSV file, really. It tells us more about the data collection, as in path to the files, path to the objects, and also the metadata elements that you specify in the catalog specification. This catalog CSV file holds the values. For example, if you had experiment ID in the specification, the catalog would tell you what that experiment ID is for a particular data set. So that's, in summary, two components of the data catalogs when we talk about intake-esm. This is a quick preview of how your catalog specification and your catalog files will look like. So the blue box here is a catalog specification file, just a small snippet for demonstration. And when you hear the word schema, it again refers to the JSON file or the catalog specification file in general. So the catalog specification file here has information such as column names, variable ID, experiment ID, and path. And also it tells what kind of data it is, what is the data format, which is described under assets. In this case, it is an etcdf example. So now looking at the yellow box, that's the catalog file for in the sense that the column names that you have in the catalog specification file actually has values in your catalog file. Experiment ID has values, and there are two different variable IDs specified in the catalogs and this absolute path to each of the files. The green highlighted text is again quickly to show how simple it is to use intake-esm with its search functionality, searching across any of the columns that you have in your catalogs and filtering your original catalog, which may have hundreds or thousands of data sets, and filtering it to just what you want for your analysis. In this case, it was the variable ID filter that was used and the experiment filter to get into your analysis. This is all done in your Jupyter notebook or your Python analysis script. So you can imagine or envision having just few more lines after this to have a figure such as this, where you're reproducing IPCC chapter figure, or you're having a multimodal analysis studying the ocean heat content. So this is an example to show you how the search blends in with your analysis pretty seamlessly. So with that as a very quick introduction to data catalogs, we'll move on to a notebook example. We will have all of these slides in the description box below. With that, we'll look at the notebook example. This is going to be a very quick walkthrough of a Jupyter notebook that uses intake-esm to search and then just directly leads into the data analysis section. In this case, it's a simple visualization using matplotlib. So the first thing you would want to do to use intake-esm is to be able to import intake and intake-esm packages. This is because intake-esm is available as a plugin to intake. The rest of the packages, whatever you need for your Jupyter notebook analysis or a Python-based analysis, you would import it here. The second thing I want to highlight here in this notebook is using intake.openesm data store. You pass the URL to your JSON file, which is the catalog specification file. The JSON file has pointers to the CSV file, so that way it's connected, and we'll be able to look at all the information in the catalog. So once we do this, this call is actually available to you as a pandas data frame. So you do a call.df, and then any information that's in your CSV is now translated or kind of translated into a pandas data frame for us to search things on. All right, I'll skim through this. So if you're curious as to what column names are available in the catalog, what can I search based on, then you can either look at the JSON file, which has the column names listed there, or you can programmatically just do call.df.columns, which will result in all the columns in your catalogs, or in this case, the pandas data frame. For example, experiment ID, realm, frequency, variable ID. These are some of the things that we'll be using in this particular notebook. One other thing, if you're curious as to how different files, different objects are aggregated or concatenated to a single XRA dataset object, you can either look at the aggregation settings in your JSON file or quickly look at this particular value in this particular key in your dictionary. So this will tell you that it is actually grouped by these columns: source ID, which in our case is model, experiment ID, frequency, realm, and chunk frequency. And these are settings that are flexible based on how you generate these catalogs. In my example, the CSV and the JSON files were generated using the GFTL catalog builder. So to be the aggregated data set would be unique combination of all of these columns. In other words, a join is performed with pandas. Okay, without getting into those details, one other thing to note is that this aggregation control also tells you that we are joining across a particular attribute or dimension, and here it is time, which means when you're concatenating, it's concatenating across time. So let's do a quick search here. And in my search, these are the simple things I'm looking for. I'm looking for the variable rsdt belonging to this realm or component, and I want only the PI control experiments. I'm also filtering based on the frequency. So then you would do a call.search and pass all those key and values. Run it again, and you will see that this catalog now has one data set resulted from 130 assets, which means 130 files, since the PI control run has been aggregated and concatenated into one data set that you can work with directly using Xarray now. Another thing to note is also that you have to use the to dataset dict here, which really results into an organized dictionary with keys being the dataset names and the values being the corresponding Xarray dataset object. So in this case, when I print out the dictionary keys, I have only one variable that I search for, so it's this. If I had searched for more variables, the key would still be this, because that's how my aggregation was set up. But when I actually open the Xarray dataset object, this is how it looks. And here under data variables, if I search for TAS, you will also see TAS here, which means you have access to RSDT and TAS from the single Xarray dataset object. And the way you access it is by just doing ds.rsdt, which is now using the data array within the Xarray dataset object itself. From here on, you can just use this Xarray in your analysis like you normally do. In my case, I just do a simple plotting with matplotlib. Hope you like this tutorial, and look for the description box for documentation and slide references. We appreciate your feedback. We appreciate your collaboration and engagement. Thank you.